away from the zone boundary. So we see here the three different materials that at a certain onset of strain, then we start to see the Dirac cones appearing. This characterizes how far away they are, and they do move away. So this is consistent with altimetry analysis. And because of the nice linearity of the Dirac fermions, we can make this identification of strain, of the effects of strain with a gauge field. Whereas in the case of non-relativistic fermions, there would also be additional terms of k dot a, and so the identification is not as smooth or straightforward in that case. So here is where we see that the lattice symmetries then give rise to different number of independent coupling constants for the strain, such that this allows us to write down for a particular valley. For a particular valley, we can write down the effects of the vector potential, and it's given by the strain tensor and the coupling constant. So all of that was for strain generically, and now we can look at what happens in particular. What is the profile of the strain as we do get in these bilayer systems? We had seen from Vidya's very nice animation how the difference in the lattice constant between these two materials gives rise to causes the buildup of strain, and this strain is then can relax through the formation of dislocations, so edge dislocations, where you should imagine a whole row of atoms that are now missing running through the system. And these rows of dislocations occur at periodic intervals, as can be seen from this TEM image, which is now seen from the top, in which there's a superlattice of dislocations. And so you can see that one of these blocks is probably on the order of 10 nanometers, so that's about 10 unit cells in this. And you can see that this is a really nice, regular array of dislocations, which is pretty cool because often we think of dislocations as being a large uncontrolled strain to the system that it's going to be very difficult to predict the results of. And in this case, because it's so nicely organized instead, that it does alter the electronic properties in a way that we can model. And you can see that the strain, that these dislocations occur in both axes, in both directions along the crystal axis. So having said that, we can go ahead and model this, and we can consult classical strain theory to give us what is the strain profile from a single dislocation, and sum them up because they occur in a regularly spaced distance apart, to obtain the total strain profile. And this is along one mirror axis, and then of course we have similar behavior coming from the other mirror axis. And again here we can, since we know the material parameters such as the Poisson's ratio, the lattice constant, etc., then we can actually estimate what kinds of strain we expect here. And we can put this into our equations. We have both the coupling, well, the degree to which strain couples as a gauge field, and the strain field itself, and we can take the curl to then obtain a resulting magnetic field. And so, looking at the numbers that we have maximum fields in the order of a couple hundred Tesla. And again, because we have to take the curl here, we do need a spatially varying strain in order to produce a non-zero field. And so this comes out very naturally from the fact that we have this periodically varying strain profile from the dislocation. And this gives rise to this periodically alternating field that averages to zero. This regions a positive field and negative field. So just to contrast this with our other favorite Dirac system, graphene, in which they also have seen pseudomagnetic fields and resulting Landau levels, as you can see from this STS spectra. Some differences here is that in here the nanobubbles, the strained nanobubbles occur in localized regions, so individual nanobubbles. And instead, in contrast, our system, because the strain is produced by this dislocation array that actually covers, as you saw,